Hello and welcome back. Today is the second day of this week. So, what are we going to learn today? We will be talking about the properties of laser light and their applications. Okay, we have talked about these properties in the first class itself. So, we just mentioned about these properties. We did not talk about the origin of these properties, and we also talked about the applications of laser light, but we did not directly relate the properties of laser light to specific applications. So, we will try to do that in this class bit briefly. Okay. So, we are going to deal with the properties of laser light and their application. So, the first thing that we will learn today is the directionality and we will also learn about beam width. So, the first thing that we will talk about is the directionality. So, in the very first class we said that laser light has a very high directionality. So, it does not spread. Okay. So, if you take any light, normal conventional light, so that is isotopic in nature, right. So, it goes in every direction. So, if you are close to the light source, the amount of intensity that you will get, if you are little away, your intensity drops, because they are always diverging, okay, because they are going in every direction. So, if you are looking at a conventional light, you do not get the directionality which you actually get in case of laser. Now, the origin, what is the origin? Okay. So, I am pretty sure that by now you yourself can figure out why there is a directionality, because we are using a cavity and there is an axis of the cavity, and the light, the photons which are getting amplified must fall along this or they should have their propagation direction along this axis, okay, or the range that is provided by my laser cavity. So, if I have my cavity like this, then it is essentially guided by this physical dimension of this mirrors. So, as we have shown in the one of the previous classes, so and ultimately it goes out, okay. So, the spontaneous photons which have their k vector lying parallel to this and falls within this width will be amplified, and they will be keeping their direction in this direction. So, when they come out, they have no other option but to follow this direction, okay. So, this is the reason when that we see that they have a very large directionality, right. Now, along with this directionality, there comes another thing, that this laser light it has a width, and this is like a rail track, right. Okay, if I take this a cross section of this beam, and then so if I take a cross section along this is a something like this, right, solid. So, if I take a cross section, I will see that you know if I take a cross section here and if I take far here, I will see there this length is pretty much the same. That means it is pretty much like a beam. We have been talking about beam, but why do I say that it's a laser beam? Why don't I just say laser light? Okay, because it is kind of collimated. Okay, so the photons are coming like a physical beam. What is the difference between say steel beam or say any other metal beam to this photon beam coming out of laser is that in case of metallic beam we have a physical barrier or physical boundary, right. So here in this case we do not have a physical boundary. So when we talk about laser beam, we do not have a physical boundary. We don't have. So in a metal beam we define the beam width, okay, always. In this case also we have to define a beam width, which is a very important characteristics of a laser light, because that gives rise to certain other properties. So it dictates like how small you can go in terms of spot diameter when you try to focus the beam, okay, using certain optics. Now how do you define a beam width for a laser beam? So our job is to define beam width for laser light. How do I do that, or what is the normal practice? The normal practice is to start with the center of the laser beam. So this is my center of the laser beam, okay, and I know that there is no physical boundary, like I have drawn very nicely here, one line here, creating a boundary, but there is no physical boundary as such. So now before going into that, we must tell that this beam properties are also associated with the mode of laser light, okay. Which mode? It should be the transverse electromagnetic mode. So this is related to a TEM mode. So the simplest thing is to look at a mode like TEM 00 mode, which I showed in one of the previous classes. So if I look at the beam profile on a photographic plate, it will look like a circle, okay. So I just mentioned that there. Now what will you find out if you look at the intensity distribution pattern here, okay. So one thing, of course, there is no node going across this, but what you will see is if you take this cross section or if you take this cross section and plot the respective intensity, you will see something like this, pretty much like a Gaussian. So this intensity profile, if you look into the 3 dimension, so you will see a Gaussian profile, okay. So the central part is the most intense and then it is falling off in this, okay. So in such a beam, we can very easily define the beam width by, so how? So the radius of the beam, so laser beam is defined as follows. We start from the center, okay. So if this is my say laser beam cross section. Okay, so laser is propagating in this direction, I am taking a cross section and I am nicely drawing this line, but we know that there is no physical boundary here. So, how do I define? I start from this center and I go to a distance radially, meaning I go in this direction or this direction or this direction or this direction. In this case it is very simple because it is symmetric all around, right. So, if I go radially and go up to the level, up to the distance, okay, where the intensity, say this I c corresponds to the intensity at the center, that means intensity here. Now, if I go a distance where the intensity falls off by E square of this intensity. Okay. So, essentially at a distance where the intensity will be I c by E square. Okay. So, that distance, say that distance is here, then I will say this is the radius of my beam, and this E square is roughly 13.5%. So, in other words, I can say that if I start from this center of the beam and keep going radially until I see that the intensity has fallen down to 13.5% of the intensity here, I will define that as the radius of my beam. So, that beam width will be 2r, that is the diameter, correct. So, this is how I define the beam width. Now, in typical numbers, if I look at, the lasers can have beam width of a millimeter to a centimeter. Okay. So, knowing that this laser has a beam width and laser has a directionality, we can also look into the divergence of the laser beam. Now, many lasers, they do not diverge pretty much. Okay. So, say for example, a typical value of beam divergence will be approximately 1 millirad. So, when I say a beam has a divergence of 1 millirad, what does that mean? That means if I start with a beam width of 1 mm, it will appear to be, sorry, this is 1 millimeter, it will appear to be 1 meter at a distance of 1 kilometer. Okay. So, it will, if we start from 1 millimeter, we will see the beam to be as 1 meter at a distance of 1 kilometer. So, you can see that the divergence is really little. Okay. It is not huge. If you take a flashlight, you will see that if you start with beam diameter of say 10 millimeter, within few meters it will be like 1 meter, right. So, this laser light is really good in terms of the divergence, and this divergence can be even smaller. Now, where do I use these properties, that is directionality and having a collimated beam with a very low divergence? In industry, people use it for alignment of various different tools or equipments using laser light because of these properties. Of course, in fundamental optics, spectroscopy, people regularly use this one, but apart from that, in a industrial scale, laser light is always used to do that. Second thing is that in the environmental studies, particularly detecting the pollution, these properties are very much needed. Okay, so I cited a particular value of divergence. One can have much less divergence. Okay, so if you want to know the condition of environment at say troposphere level or beyond, then you can use laser light because they are highly directional, they are low on divergence, and they have a definite beam width. So you can use laser light to do pollution detection, measurement, etc., and even in astrophysics. Now, one more thing is that if we take this kind of beam, we can also focus it to a very tiny spot by using a convergence optics like lens. Okay, so for a beam like this TM00 with a TM00 mode, we can have a spot dimension, say omega 0 or W0 as 2 lambda by pi theta. So I am talking about focusing the beam. So essentially I have a parallel beam going, put a convergence optics, focus them. Now many of you know that we can focus it up to a certain dimension. We cannot really zero on a point. Okay, so there will be a beam waste, and then it will diverge. Okay, and this is my beam waste. Okay, so and this is my angle of convergence, theta is related by this one. So you can get a particular spot diameter. Okay, so this is the beam waste. Now we can go to very small value of W0, okay, the beam waste, which is very difficult to do with a conventional light. Okay. Now what is the application of this property, that I can really go to very small focal spot? In industry, you need to achieve really high intensity light to cut or weld or to melt things, okay, particularly metals or leather, various other stuffs. So there you can get that high intensity by focusing it. It is well understood that if you start with a large beam and then if you focus it, then all the photons are actually falling on that particular small diameter, which is denoted by this. Okay, so there you find the application of these properties. Now we will move to another one. Second property is intensity. So this is probably one of the most important aspect of laser which has been utilized in industry. Okay, so just 1 minute ago I talked about focusing a beam so that we can intensify the beam, and we can use it for cutting metals or doing various other processing work in industry. So how do I define this intensity of laser beam? So this laser beam is collimated. Okay, so they are going in a particular direction. It's like a parallel beam. So in such case, we define intensity in much better way by utilizing or by using irradiance. So, what is irradiance? Irradiance is given by uh, energy by time by area. So, energy per time per area. Okay, so this is a lot easier to quantify the intensity of laser because they have a parallel beam going with very low divergence. So, this one I can write simply as power, this energy per unit time is power by area. So, essentially this is power per unit area. So, what will be the approximate dimension? I can write watt per meter square. Okay. All right. So, now we have to look at the irradiance values of lasers. Okay. Now, to put things in the right perspective, we should also have some reference value. So, what can be the best reference other than the sunlight? Okay. So, for sunlight, if I consider 1 meter square area, then the irradiance value. So, irradiance is written as I. Okay. So, for sunlight I have I value on earth is typically 10 power 3 watt per meter square. Okay. This is on earth surface. So, this we should know so that we can compare how low or high the laser intensity is in terms of irradiance. Okay. So, we will talk about couple of different cases. So, let us say let us take argon laser, okay, argon ion laser, which which can give various different frequency. So, let us take 480 nanometer output. Now, argon ion laser is known to give moderate power, okay, not very high power, and it is a gas laser. Now, at this particular wavelength, say we have a beam width of 1 millimeter square and power of 1 watt. Okay. And this I am talking about an average power. Okay. What is average power, peak power, we will learn soon. So, we will define those terms. So, now for this system, what will be the irradiance? So, irradiance will be power by this one, right. So, 1 watt by 1 millimeter square. So, 1 millimeter is equals to 10 power minus 3 meter, so square. So, essentially this is okay. So, typically it can be 1 watt. So, it will be 10 power 6 okay, watt per meter square. So, a beam of argon ion laser which has an average power of 1 watt and a beam width of 1 millimeter square has an irradiance of 10 power 6. Immediately you can compare these two values, okay, for sunlight and for this argon ion laser. Now, what will happen if you focus this beam? So, if you focus the beam, you can go to really small diameter, you can calculate that from this. Okay. So, if you find out that beam waist, you can probably increase this irradiance by another 10 power 6 times. Okay. So, you can easily calculate that one. Okay. So, if you take say like if you talk in terms of the diffraction limit, because the beam cannot be focused down to a spot. So, there is a limit. Typically this is the diameter of the beam is approximately lambda by 2, lambda is the wavelength of light. Okay. So, if you consider that and 488 nanometers, so typically say I say like 250 nanometer, if you convert that into area, I mean assuming a circular beam, then you will see for focused beam you have I equals to 10 power 12 watt per meter square, which is really high. Okay, much higher than the irradiance of sunlight on earth's surface. If we consider something like a ruby laser, which is a pulse laser having a pulse width of 25 nanosecond. Okay. So, next class probably we will talking about some of these, so like pulse width and all. So, say probably I have mentioned it earlier. So, if the light comes in pulses, so and this is my time axis and this is the intensity. So, this width is my pulse width. Okay. So, if for ruby laser it is 25 nanosecond, and if I take typical power of say 10 watt, then we can find out the irradiance by knowing the beam diameter. So, the beam area of a ruby laser is slightly larger, is approximately like 500 millimeter square. So, if we take that, we have to normalize with respect to this time, because its power is per time, right, energy per time. So, you will see that overall an unfocused beam, that is a collimated beam of ruby laser, it gives an I value of 10 to the power 12 watt per meter square, and when you focus it, it goes to 10 to the power 18 watt per meter square. So, it is huge amount of intensity, and this have been the property which the industry really capitalizes on. Okay. Because of this high intensity, it can cut almost everything and anything and everything. So, for example, if I take a laser beam of say if I take something like Indiac laser and we consider an intensity. So, if I take Indiac laser and consider say 10 watt per meter square, and we can use this to cut a steel plate having a thickness of 3 mm at a rate of 1 centimeter per second, which is really rapid. Okay. So, these are certain unique applications of these lasers because of their properties like high intensity. So, there are a couple of more properties that we need to quickly discuss. One is the coherence, another is the monochromaticity. So, we have to stop today because of lack of time. So, in the next class we will start with those two properties and looking at their applications. We will also learn how to actually estimate the number of modes corresponding to one particular gain bandwidth. So, we will talk about all these things in the following class. Thank you very much.